Okay guys, in this video we're just going to work through another example of solving a polynomial inequality, and I'm just going to kind of go right through the steps here. So let's take a look at number 14. As a matter of fact, 14 compared to number 10 that we did a moment ago, one thing I do want to point out to you is that the last inequality was greater than or equals to. In this case we just have a greater than, which is going to play into our solution intervals here. Let's go ahead and do this. Let's go ahead and get it set to 0 on one side. So I'm going to call this 2x squared. I'm going to say plus 5x plus 3 is greater than 0. And again, we want to, if at all possible, factor the left-hand side. And so I notice that this is a factorable thing here. There is no GCF, but if we were to set this up so that I have a 2x and an x in front, I'd have my 2x squared. And then factors of 3, I suppose, plus 1 and plus 3. Now we can check this out. You'll notice that if I try to FOIL this out, I get 6x and 1x is 7x. So that doesn't work there. So maybe instead what we'll do is we'll try plus 3 plus 1, and I notice that this works instead here. I'd get 2x plus 3x is 5x. Okay, so we got a 0 on one side and we factored the other side. So what we're going to do is first of all, we're going to list our critical values. Now these are the zeros of our function here. So if I were to say what are my zeros that correspond to these two factors here, I would say that setting 2x plus 3 equal to 0 and solving it, I get negative 3 halves. Or in other words, negative 1.5. And setting x plus 1 equals 0, I get negative 1. So now that we have our critical values, what we're going to do is we're going to set up our number line. We're going to place these values on the number line. Now I notice they're both negative, so I'll just go ahead and throw a 0 right here. And maybe I'll just say this is negative 1, negative 2, negative 3. How about it though? I'll label this negative 1 and negative 2. So our critical values here, maybe I'll mark them in a different color. Maybe we'll go for like a greenish. So I would say that at negative 1 and at negative 1.5, we have critical values. And so we're going to set up around these our test intervals. Now if I have two critical values, it means that I've split up my number line into 3 different intervals. So our test intervals, let me go ahead and get a little subsection set up for this here. We say, well then what would my test intervals be? So our first test interval would be from negative infinity all the way up to this negative 1.5, which was one of our zeros here. Our next test interval would be from negative 1.5 just to negative 1, so a very short test interval. And then our last test interval would be from negative 1 out to infinity, positive infinity. So as we normally do, what we're really doing is we're just going to pick an x value from within each interval to go test back into our factored inequality here. So I'm going to test to the left of negative 1.5. I'm inclined to test negative 2. Between negative 1.5 and negative 1, how about negative 1.25? Not a lot to choose from, so this is a nice rounded off number here. And then we say to the right of negative 1, I'd be crazy if I didn't pick 0. So remember that I had mentioned earlier that if you're going to test these, it is advantageous to test them in your factored form, because really we're really just comparing things to 0, and all I really care about is does the expression on the left come out to be positive or negative. Let's check out what we get here when we plug in a negative 2 into our factored expression. So what I get is 2 times negative 2 plus 3. And this is negative 2 plus 1, and this is greater than 0. So what I end up with is this negative 4 plus 3, which is negative 1, times negative 2 plus 1, which is negative 1. And so in this case, we get a negative times a negative, which is certainly a positive, and a positive is greater than 0. So since this is true, we are going to keep this interval right here. So I'm just going to put a box around it for right now. Now heading over to our middle interval here, we're going to test negative 1.25. So 2 times negative 1.25, and we're going to say plus 3. And this is negative 1.25, suppose plus 1, and this is greater than 0. So we're going to have to borrow some space from our last interval here. But what I find out is I suppose I get negative 2.5. I'll actually show my work here, plus 3. And then this is negative 1.25 plus 1, so negative 0.25. This is greater than 0. In other words, what I get is a positive times a negative greater than 0, which would be false because a negative is not greater than 0. So we would say this is false, but also that every x value on this interval would also have to not satisfy the original inequality. So last but not least, let's test 0 here. And when I test 0, I get 2 times 0 plus 3 times 0 plus 1 is greater than 0. In other words, I get 3 times 1 is greater than 0, which is totally true. A positive is greater than 0. So this is true, true, and that means that we're going to accept this last interval here. So the last thing we wanted to do here was state our solutions and graph the solution set. So solutions wise, we know that these are the two intervals that cause us to have true statements. Now the question that I have before we decide on how to write these two intervals is, should we include negative 1.5 and negative 1? Now keep in mind that negative 1.5 and negative 1 are the zeros of this function. So if I'd go plug them into this function, I get 0. And that would be a problem because in this case, I would be saying 0 is greater than 0, which is actually false. So it is going to be true for all x values in these two intervals here that occur to the left of negative 1.5 and to the right of negative 1. But what we find out is that I can't include negative 1.5. And so when we graph our solution set here, we're going to say I use parentheses on these two sides. And also when we list our solution intervals here, we're going to say negative infinity to negative 1.5, but don't include negative 1.5. And this is in union with negative 1 to infinity. So here is our solution set, and this is our graph right here. Cheers.